let me again start with defining a problem. So two sample tests we need if we would like to find out how likely two samples came from the same population, right? From the population with the same properties, so to speak. So the populations have same distribution. The parametric solution in this case will be two sample t-test for the mean, and non-parametric solution is called Mann-Whitney U-test. However, it has another name. It's called Wilcoxon rank sum test. So therefore, you will find out that in R, for example, it's called Wilcoxon test, not Mann-Whitney test. But they are the same. There are some differences how to compute statistics, but when you compute it, it will be the same statistic and the procedure will be the same. So therefore, I will show you the algorithm which from the Mann-Whitney U-test because it's a little bit simpler. Okay. Now let me again make an example. This time I will use a new data set, and in this time I will use data set which is not good for parametric approach. You will see why. Let's still keep this idea about testing tablets, but in this case I would like to compare tablets from company A and B and find out which of these, is there any difference in how long they can work without recharging. Okay, so this is my data set. This is results of 10 tests I carried out for tablets produced by company A. This is the results of also 10 tablets produced by company B, right? So this is the hours, how long they could work just by watching YouTube videos, okay? And then if you make plots, you will clearly see why it can be problematic for parametric approach, right? For example, let's start with this strip chart, right? So you can see that, for example, the B has the smallest and at the same time the longest time, okay? And then you can see that the variation is quite big because of these two outliers. Here you also have a couple of outliers. Also, if you look at the plots, especially on this plot, on the box plot, right, you can clearly see that kind of distribution of this time is shifted comparing to the distribution of this time, right? So we can say that the shift between two distributions is not zero. They are shifted. What is shift? Shift, it's a chance to find a value. For example, if you take a random value here, how likely or how many values from here will be smaller or larger than this one, right? So if distribution are more or less the same, then this probability will be 0.5, right? Some of the values will be larger, some of the values will be smaller. So this is the case where shift is 0. So let's find out how likely these two samples came from populations where the shift is 0. But starting from this example, I will use a significance level on 0.05 because I will save on sample size, just for illustration purposes. Otherwise, you will have a lot of numbers on your screen and it will be difficult to follow the examples. Okay. So if I make a parametric test, in this case, it will be two sample t-test. This is the result of two sample t-test. You can see I enter A, I enter B, and then I ran two sample t-test. Then you can see the p-value is 0.15 or 0.16 in this case. So there is no statistical evidence that this population have different means, at least, right? So from that point of view, we conclude that this population have no difference. The samples came from this population, so all tablets produced by these two companies. But let's see what non-parametric approach will tell us. This is the whole procedure. Again, you can see 6 steps. I will not explain the steps right now, but we will show you this gradually. Okay. So, step number 1, merge all values from both samples and ranks them. So it means that when we compute ranks, we shouldn't compute ranks individually for A and B. We should merge them like it's one big sample with 20 values. And this is the merged values and the ranks. You can see, for example, where is the smallest time? This is the smallest. Where is it? It's this one, right? So this is the smallest time, and that's why it's ranked number 1. But the next smallest time, it's here. You can see it in sample A, and this is ranked number 2. Then you can see, in general, sample from company A have pretty small working time, right, comparing to the samples from company B. But is it small enough to get a significant difference, statistical evidence? We will see it. Now we split ranks again. So now we have them ranked separately, ranks for A and ranks for B. And what we do a very interesting thing. For every rank in A, for example, let's take this one, 6. we compute how many rings in sample B here are smaller than this one. So how many rings in B are smaller than 6? This is not smaller, not smaller, not smaller, not smaller, not smaller. This one is smaller, right? So 1. And that's why this is 1. So this is what is called UI value. Okay. This is the new ring, 19. How many values smaller than this one? Well, this is smaller, this is smaller, this is smaller, this is smaller, this is smaller. This one is smaller, this one is smaller, this one is smaller, this is not. This is smaller, so it's 9. So we write it 9 here. And then we simply continue. And these are all these values where rank in B is smaller than this rank in A. Okay. After that, we simply take a sum. Again, sum. You remember sum of ranks and so on. So we going towards the normal distribution again, right? So this is our statistic. Sum of these counts is 23. Now we need to find a p-value, but again we need to find a p-value if we can find a p-value if we know which distribution this particular statistic follows, and also how to compute, for example, parameters of this distribution. Same idea. If number of values in each group is larger than 20, equal or larger than 20, again I don't my sample is too small for this test, but it will work anyway, so you will see it in a minute, right? Then this distribution is normal distribution, so your statistic follows normal distribution, and then this is the average, expected U value, so to speak, from your samples, and this is the variance of these U values, so it's how far these values can go from the average, right, from the expected. Here I must say a couple of things. First of all, if sample size is smaller than 20, then we cannot use normal distribution, and there are some tabulated values, so you still can find distribution of U, but it's not, it's a bit complex, and therefore there is no, for example, function that implemented in R that you can use to calculate all these statistics. There are some tables, okay? That's one thing. The second thing, when we say follows normal distribution, it means approximately. So it's not precisely, but approximately follows normal distribution, okay? Having said that, let's compute the average and variance and standard error. So this is the average. You can see I simply take a sample size in A, a sample size in B. In my case, it's the same, 10 and 10, and then divide to 2, it will be 50. So if null hypothesis is true, so distributions are equal, then this number of, so how many values here, how many ranks here are larger than these ranks will be 50, and also vice versa, actually, okay? However, of course, because it's a random sample, it can vary around the expected value, and the degree of variation, it's our standard error. So first we compute variance by just putting all these values here again, and then we compute standard error. So again, you can see standard error is approximately 13. So in 68% of the cases, the U score should be between 50 plus minus 13. In 95.5% of the cases, 50 plus minus 26. Okay. So let's see how extreme our U score is for this particular situation. So in this case, again, we compute Z score, and it tells us that the difference between the expected U value and the observed U value, it's approximately 2.04 standard errors. So it's beyond this plus minus 2, but very close to, right? If you compute a p-value, in this case, it's a two-tailed case, because our null hypothesis is that distributions are equal, no shift between distributions. So therefore, we need to find this area, right, for z-score plus 2.041, and this area for z-score minus 2.041, right? I can simply take this area and double it because they are symmetric, right? The distribution is symmetric. This is what I have done here, and then you can see that the p-value is 0.04. So in this case, we can reject null hypothesis and assume that indeed, in this case, we know it's sample, the producer A works worse than producer B, or tablets from producer A work worse than tablets from producer B, right? So because the median time is smaller. Okay. So that's it. And now if I run the test, you can see I use the same function Wilcox test. Like you remember, t-test works for one sample and for two sample. Likewise, Wilcox test function in R also works for two cases, for one sample and for two sample. And then you can see that the p-value is slightly larger than this one. Why it's larger? Because it's exactly the situation where we cannot use normal distribution, so therefore this function Wilks test has some adjustments for the small sample size. I can turn off these adjustments if I simply say correct equal to false and exact equal to false. In this case, it will not use these adjustments, it will use just a direct normal distribution. And in this case, you can see that indeed the p-value is the same as we got here. Okay. But of course, don't do it in reality. If you have a small sample size, it's a good idea to adjust the p-value. Okay. So that's it. Again, you can see a very simple way to t-test. Of course, the procedure is different and more complicated, but again, it's not a rocket science. If you understand how ranks work, then it's not a problem. It's just a simple mathematics. Okay. So that's it. Now you know also how to compare two samples. In the next video, we will discuss how to compare more than two samples.